Welcome to All Sorts Podcast. Today we're really diving deep into something fundamental, band gaps in materials.
That's right. It sounds technical, but it's crucial.
Yeah, it basically governs how, electronics and optical stuff works, like your phone, solar panels, everything.
Exactly. It dictates behavior at a really core level.
And we've got some great source material to help us unpack this. We're looking at the Wikipedia page on band gaps, naturally.
Always a good starting point.
And then a Nanoletters article, Band Gap Engineering of 2D Materials Toward High-Performing Straintronics. Sounds cutting edge.
Oh, it is. Straintronics is a fascinating area.
Plus, a paper from the International Journal of Scientific Research in Engineering and Management on quantum dots, specifically Ti-Fe, 3-5Fe, and 5e semiconductor quantum dots.
Quantum dots. Size really matters there.
And finally, a review from Industrial and Engineering Chemistry Research about actually making these quantum dots colloidal synthesis.
So, from the theory to the practice and the latest applications, a good mix.
Exactly. Our mission today, figure out what band gaps are, why they're so important, and how scientists are actually tweaking them for new tech.
Let's do it.
Okay, so first things first, what is a band gap?
Well, at its simplest, it's an energy range inside a solid material where electrons, well, they just can't exist.
Can't exist, like forbidden.
Precisely. Forbidden energy levels. Think of like an energy staircase for electrons. The steps are allowed, energy levels, the energy bands.
Okay.
The band gap is the empty space between certain steps. An electron can be on a step, but not hovering in between.
So it's a literal gap in possible energies?
Exactly.
Yeah.
And we usually talk about two main bands involved here. The valence band.
Right. That's usually full of electrons.
Mostly full, yes. It's where the electrons normally hang out. And then above it, energetically speaking, is the conduction band.
Which is normally empty.
Mostly empty. And the band gap is the energy difference, the energy an electron needs to gain to jump from that valence band up into the conduction band.
And that jump is the key, isn't it?
Absolutely. Because once an electron gets into the conduction band,
it can move around? Conduct electricity?
Precisely. It's free from its specific atom. It can move through the material. And when it jumps, it leaves behind a kind of vacancy in the valence band. We call that a hole.
Ah, the hole. I've heard of that. It acts like a positive charge.
Effectively, yes. The hole can move, too, as other electrons fill it, so it also contributes to conduction.
So the size of this energy gap, that determines everything.
It's a major factor, yes. If the gap is really large, electrons need a huge energy boost to jump.
So they stay put. Insulators.
Exactly. Materials with large band gaps generally say over 4 electron volts are insulators, like glass or diamond. It takes a lot to get electrons moving in those.
Okay, 4 eV. Got it. And if the gap is small?
Then you get semiconductors. It takes less energy to get electrons across so they can conduct under certain conditions, like with heat or light.
And if there's no gap, or the bands overlap?
Then you have a conductor, a metal. Electrons can move very freely with almost no energy input needed.
So the band gap is really the gatekeeper for electrical conductivity.
You could say that, yeah.
And you mentioned earlier it relates to chemistry, too, like HOMO-LUMO.
Yes, it's conceptually very similar. In a molecule, you have the highest occupied molecular orbital, the HOMO, and the lowest unoccupied molecular orbital, the LMO.
Analogous to valence and conduction bands.
Exactly. The HOMO-LUMO gap determines how a molecule reacts, absorbs light. Much like the band gap determines a solid's electrical and optical properties, it's the same underlying quantum mechanical principles at work, just scaled up from a molecule to a whole solid.
Fascinating. So this structure, these bands and gaps, they're unique to each material.
Absolutely unique, like electronic fingerprint. That's why we have such a vast range of electrical behaviors in materials.
And the Wikipedia source mentions something about dimensions, 1D, 2D, 3D materials having different band structures.
That's right. The dimensionality plays a big role. A material's band structure and even how it interacts with light, its spectroscopy, can change quite significantly depending on whether it's a bulk 3D crystal, a flat 2D sheet, or a thin 1D wire.
So you can't just assume a thin film will act exactly like a big chunk of the same stuff.
Definitely not. For instance, in 1D nonmetallic solids, the optical properties are really dominated by electrons jumping between the valence and conduction bands.
Okay.
And the probability of that jump, how likely it is to happen when light hits it, depends on a specific quantum mechanical calculation, an integral involving the electron state before and after the jump, and the light's electric field.
So it's not just about having enough energy. The transition itself has to be sort of allowed quantum mechanically?
Exactly. Momentum often plays a role, too, which we'll probably get into with direct-indirect gaps later. But yes, the quantum rules have to be satisfied.
Okay. So how do electrons get this energy to jump the gap? Heat and light you mentioned.
So those are the two main ways, yes.
Yeah.
An electron can absorb a phonon.
A phonon. That's like a packet of vibration. Heat.
Precisely. Lattice vibrations. As the material gets hotter, atoms vibrate more, creating phonons, and an electron can absorb that energy.
Or it can absorb a photon. Light.
Yes. If a photon comes in with energy equal to or greater than the band gap energy, an electron in the valence band can absorb it and get promoted to the conduction band.
That's the basis of solar cells, right?
Huh?
Light creates charge carriers.
Exactly that. And it perfectly leads us into band gap engineering.
Ah, yes. Controlling the gap.
If the band gap dictates properties, then being able to change or design the band gap,
Oh.
well, that's incredibly powerful.
How do scientists actually do that? It sounds almost like alchemy.
Well, it's very precise science. One major way is by creating semiconductor alloys.
Mixing different semiconductors together.
Exactly. You carefully control the composition. For example, mixing gallium arsenide with aluminum arsenide lets you create gallium aluminum arsenide, GaLiAs. By changing the ratio of gallium to aluminum, you can tune the band gap smoothly between the values for pure JAs and pure alloys.
So like tuning a recipe? Other examples?
Oh, yes. Indium gallium arsenide, NGAs, indium aluminum arsenide, ALAs. These are workhorses in semiconductor technology.
And another way, layering materials.
Yes, using techniques like molecular beam epitaxy or MBE.
That's the ultra-precise atom-by-atom deposition.
That's the one. You can grow incredibly thin layers of different materials on top of each other with atomically sharp interfaces. This allows you to create structures called heterostructures, where the band gap changes abruptly from one layer to the next.
Creating quantum wells and other structures.
Exactly. These engineered structures are crucial for advanced devices.
Like what? The Wikipedia source mentioned some?
Right. Heterojunction bipolar transistors, HBTs, which are vital for high-frequency electronics, like in cell phones, laser diodes, the lasers in Blu-ray players, fiber optics, and of course, optimizing solar cells for better efficiency. All rely heavily on band gap engineering.
It's incredible. Now, going back quickly to semiconductors versus insulators, you said semiconductors are like insulators with smaller gaps.
That's a helpful way to think about it, yeah. The line isn't perfectly sharp. It's more of a continuum defined by the gap size. Semiconductors just have gaps small enough that electrons can be excited across them under reasonable conditions.
But Wikipedia also mentioned electron mobility plays a role.
It does. Mobility is how easily electrons, once they are in the conduction band, can actually move through the material. You could, in theory, have a material with a reasonably small gap. But if the electrons get scattered or trapped easily, its conductivity will still be low. So both the gap and the mobility matter for the overall glassification and performance.
Okay, that clarifies things. Now let's shrink down. Quantum dots. The paper on those highlights that size is the defining factor for their band gap.
It's truly one of the most fascinating aspects of nanoscience. Quantum dots are tiny semiconductor crystals, maybe just a few nanometers across.
Really tiny.
And when you get down to that scale, something called the quantum confinement effect kicks in.
Quantum confinement, meaning the electrons are trapped spatially.
Exactly. Their movement is restricted in all three dimensions. Electrons in solids have wave-like properties. When the crystal size becomes comparable to the natural size or wavelength of the electron, specifically something called the exciton Bohr radius, the electron feels the boundaries.
Like a wave in a small box.
Precisely. And just like waves in a box can only have certain frequencies or energies, the electrons in the quantum dot can only occupy discrete, quantized energy levels.
So no more continuous bands like in bulk material.
The bands effectively break up into distinct levels, and the energy spacing between these levels, which acts as the effective band gap, becomes strongly dependent on the size of the dot.
And crucially, smaller dots mean larger gaps.
Yes. It's a bit counterintuitive, but the stronger the confinement, smaller dot, the further apart the energy levels are pushed, leading to a larger effective band gap.
So you can literally tune the band gap, and therefore the properties, just by controlling the size.
That's the magic of quantum dots. By making them slightly larger or smaller, you can precisely select the energy gap. This overcomes the fixed band gap limitation you have with bulk semiconductors.
Which means you can tune the color of light they emit or absorb.
Exactly. Smaller dots absorb and emit higher energy light blues and greens. Larger dots absorb and emit lower energy light reds and oranges. This results in a blue shift in the optical properties as the size decreases.
And the paper mentions this is great for things like displays and medical imaging.
Absolutely. Quantum dots can absorb light over a broad spectrum, but then emit light in a very narrow specific color determined by their size. This sharp emission is fantastic for creating vibrant, pure colors in QLED displays.
And for imaging.
You can inject different sized dots, maybe tagged to different biological targets, excite them all with one color light, and then distinguish them by the specific colors they emit. It allows for multicolor detection and imaging. Very powerful.
The paper listed some specific QD materials, too.
Right. Things like cadmium selenide, CDSE, and cadmium sulfide, CDS, are known for bright visible light emission.
Uh-huh.
Gallium arsenide, GAAs, indium arsenide, NEAs, indium antimonide, NSD, are good for visible to near-infrared applications.
And for solar?
Lead sulfide, PBS, lead selenide, PBSE, lead telluride, PBTE. Their band gaps can be tuned to match the solar spectrum really well, making them promising for next-gen solar cells.
It's like a designer toolkit for optoelectronics. The paper even mentioned the quantum model behind it, particle in a sphere.
Yeah, that's a simplified but effective model. You solve the Schrödinger equation for an electron confined in a spherical potential well.
And it shows the energy depends on size.
Explicitly. The model predicts that the confinement energy, the extra energy added due to the box, is inversely proportional to the square of the dot's diameter, EA1D2.
So small changes in ED have a big effect.
A very big effect at the nanoscale.
Okay, incredible. Now, shifting gears slightly to 2D materials, the Nanoletters article focuses on these atom-thin sheets, like graphene.
Yes. 2D materials are another huge area for band gap engineering. Graphene, transition metal difalcogenides, or TMDs, hexagonal boron nitride, HBN, black phosphorus.
And the key thing here is their sensitivity. Their gaps can be tuned dynamically.
That's a major draw. Their electronic properties, especially the band gap, are incredibly sensitive to external factors. You can change the gap by stretching or compressing the material that's strained.
Right. Straintronics.
Or by applying an electric field, or by chemically modifying the surface, adding atoms or molecules. This opens up ways to actively control the material's behavior in a device.
So take graphene. It's famous for not having a band gap, right? It's semi-metal.
Naturally, yes. Pristine single-layer graphene conducts extremely well, but for transistors, you need to be able to switch the current off, which requires a gap.
So how do you give graphene a gap?
Several ways have been developed. Chemical functionalization, like adding hydrogen atoms, introducing specific defects or nanopores, putting it on certain substrates that interact with it, stacking it with other 2D materials like HBN.
Van der Waals heterostructures.
Exactly.
Yeah.
Or even cutting graphene into narrow strips called nanoribbons.
Ah, quantum confinement again. Like in quantum dots, but in 1D or 2D.
Precisely. If the ribbon is narrow enough, confinement effects open up a band gap, so you can turn this amazing conductor into a semiconductor.
What about the TMDs like MOS2 or WS2? They do have gaps, right?
They do, naturally.
Yeah.
And those gaps are also tunable. The gap changes depending on the number of layers. Monolayer MOS2 has a direct gap, while bulk MOS2 has an indirect gap, for example.
Layer-dependent gaps. Wow.
And they are very sensitive to strain. You can tune the gap size by stretching or compressing. And remarkably, for something like monolayer WS2, applying strain can actually switch it from a direct gap material to an indirect gap material.
Which affects how well it emits light, right?
Significantly.
Yeah.
Direct gaps are much better for light emission.
Black phosphorus was another one mentioned.
Yes, BP is fascinating. Its gap changes dramatically with thickness. Bulk BP has a small gap, around 0.3 eV. A single layer, it jumps to about 2 eV.
Huge difference, and also tunable with strain.
Very much so. Even just 1% strain can noticeably change its band gap, making it interesting for sensors or strain-tunable devices.
Even HBN, the insulator, strain affects it.
It does. Although HBN has a very large gap to begin with, strain can still subtly modify its electronic structure.
And that example of creating Psi2T2 films that don't exist normally.
That's a fantastic example of strain engineering. They used the strain from the substrate not just to tune properties, but to actually stabilize a completely new 2D material structure. And it turned out to have a useful mid-infrared band gap.
Which brings us properly to straintronics, using strain as the control knob.
Exactly. Instead of just using voltage, you use mechanical deformation. Applying strain changes bond lengths, vibrational frequencies.
And the band gap. Compressive strain widens it, tensile narrows it.
Generally, yes. You're literally reshaping the electronic energy landscape by squeezing or stretching the atomic lattice. It's potentially much more energy efficient than purely electrical control.
And 2D materials are ideal because they're so flexible they can take a lot of strain.
Much more than bulk materials. Bulk silicon might fracture at 1 or 2% strain. A 2D sheet might handle up to 10% or even more before breaking. That gives you a much wider tuning range.
How do they actually apply the strain in experiments?
Various clever ways. Bending the flexible substrate the 2D material is on, transferring it to a pre-stretched substrate and then letting it relax, using differences in thermal expansion between the material and the substrate, or using piezoelectric substrates.
Piezoelectric. They generate strain when you apply a voltage.
Correct. So you can electrically control the mechanical strain applied to the 2D material. It's a whole new way to build devices.
Mind-bending. Okay, another important distinction from Wikipedia, direct versus indirect band gaps. We touched on this.
Right. This comes down to momentum conservation during the electron jump.
Momentum.
Yeah, electrons in crystals have momentum related to their wave-like nature. In a direct band gap material, the electron at the top of the valence band has the same momentum as the state at the bottom of the conduction band.
So it can jump straight up by absorbing a photon.
Exactly. The photon provides the energy, and momentum is already conserved. This is very efficient. Makes for good LEDs, lasers, solar cells.
Like jumping straight across a ditch.
Good analogy. Now, in an indirect gap material, the momentum at the top of the valence band is different from the momentum at the bottom of the conduction band.
So a photon alone isn't enough.
Correct. To conserve both energy and momentum, the electron usually needs to interact with a phonon, a lattice vibration, at the same time it absorbs or emits a photon.
The running leap, grabbing the extra rock?
Yes. That three-body interaction, electron, photon, phonon, is much less probable than the direct two-body interaction, electron, photon.
So light emission and absorption are weaker. Silicon is indirect, right?
It is. That's why silicon isn't great for making lasers, but it's still the king of electronics because of its other properties and manufacturability. So indirect isn't necessarily bad, just different.
And for solar cells, the optical gap is key, determining what sunlight gets absorbed.
Absolutely crucial. The optical band gap sets the threshold. Photons with less energy than the gap pass right through, wasted. Photons with much more energy are absorbed, but the extra energy mostly turns into heat, also wasted.
So you want to match the gap to the peak of the solar spectrum.
Ideally, yes. Or use clever structures like tandem cells with different gaps to capture more of the spectrum.
Wikipedia also briefly mentioned photonic band gaps for light itself.
Yeah, a whole different field, but related concept. Photonic crystals are materials structured periodically on the scale of the wavelength of light. These structures can create forbidden frequency ranges, photonic band gaps, or stop bands where light of certain colors simply cannot travel through the material. It's like an insulator for light.
Controlling light flow like semiconductors control electron flow?
Wow.
Okay, finally, how are quantum dots actually made? The INEC research review covered synthesis.
Right. Colloidal synthesis is common, making them in a liquid solution. Hot injection is a classic method.
Injecting precursors into hot solvent?
Exactly. Rapid injection leads to a burst of nucleation, then controlled growth. Can produce very high-quality, uniform dots. But sometimes scaling it up reproducibly is tricky.
What else? Non-injection methods.
Yes, things like heating metal organic precursors, maybe metal xanthates, and coordinating solvents. Often simpler, potentially easier to scale, maybe lower temperatures needed.
And Higgs, high gravity.
That's an interesting one. Uses centrifugal force in rotating packed beds to dramatically enhance mixing and reaction rates. Aims for better homogeneity and control, especially for nanomaterial synthesis.
Thermospray, spraying droplets.
Yeah, you spray a precursor solution, the solvent evaporates from the tiny droplets, and the quantum dots form, often without needing surface ligands initially.
And biological synthesis, using microbes.
A greener approach, using microorganisms, bacteria, or fungi that can naturally precipitate metal sulfide nanoparticles as part of their metabolism. Still under development, but very promising for sustainability.
So many different ways to cook up these nanoscale wonders.
It shows how vital controlling the synthesis is to achieving those precisely engineered properties we've been talking about. Chemistry, physics, engineering, all coming together.
Absolutely. So, wrapping this up, it's crystal clear that band gaps aren't just theory. They're fundamental to how materials work for electronics, for optics.
Definitely. They set the stage for conductivity, light interaction, everything.
And the ability to engineer these gaps through alloys, through layering, through quantum dot size, through straining 2D materials, it's just revolutionary.
It really is. It's driving innovation across the board. Better solar cells, displays, transistors, sensors, medical
The
tools.
applications seem almost endless. It really makes you think. We're manipulating the very energy landscape of electrons inside materials on the nanoscale.
Precisely. And as our control gets even finer, even more sophisticated, what else becomes possible? What completely new phenomena or devices might emerge that we haven't even conceived of yet? That's the exciting frontier.
A truly provocative thought to end on. The potential seems immense. And now, dear listener, if this exploration into the heart of materials has sparked a flicker of understanding, if these insights have illuminated a new corner of your knowledge, we invite you to become a beacon for others. Like, share, and subscribe to All Sorts Podcast on YouTube, allowing these deep dives to reach new minds eager to explore the wonders of science. Journey through the vast landscape of our previous discussions, each a unique adventure into fascinating territories. And for glimpses behind the scenes and further connections, follow us on X, Instagram, and Threads. Your engagement fuels our quest for knowledge and understanding, allowing All Sorts Podcasts to continue to grow and explore new horizons. Thank you for joining us on this deep dive into the fascinating world of band gaps right here on All Sorts Podcast.